Our next speaker is Raul Angulo, and he'll speak on towards a complete cosmological analysis of large-scale structure.
Yeah. Thank you. Yes, so today I wanted to talk about the problem of analyzing large-scale structure, and in particular what we would need to do if we want to fully exploit all the future data. I forgot about that. So as we have heard in a few talks, now we are in the next decade, there will be many surveys, large-scale structure survey, essentially measuring millions of galaxies up to very high redshifts. And this is very exciting because this gives us the opportunity to do a lot of fundamental physics. In particular, we are going to be constraining neutrino masses, modifications of gravity, perhaps the dark energy equation of state, and even give us some hints about inflation. So this is very important from a physical point of view because it will be testing our understanding of how structures form in the universe, and also will give us a chance to discover new physics. But analyzing the large-scale structure is actually a very tough problem. So if we start considering, for instance, linear fields generated after inflation, we need to consider gravity, then to predict the dark matter field, low redshifts, and then all the baryonic physics that comes with it. So in the initial, or in the CMB, around the redshifts of the CMB, the fields are Gaussian linears, they follow Boltzmann equation, which we know how to solve. But later on, gravity makes the fields extremely nonlinear, non-Gaussian, and then we have halos forming, which are also biased tracers of the underlying field, and their distribution, their abundance are also dependent on non-local processes, might depend on tidal field, the full history of assembly, maybe some stochasticity. And of course, we want to compare with real galaxies, and then there are a bunch of other effects, right? We have galaxies themselves are biased, we measure redshifts, not distances. There are, that involves velocity fields, which in turn are also non-linear, non-Gaussian, non-local, and so on. And there are also all sorts of observational issues that perhaps we don't even know to write a livelihood. So the current way that we approach the problem is that for a given input cosmology, we use some flavor of perturbation theory, then we model galaxies with some analytic function, and then we typically compute correlation functions in either real or Fourier space. But this approach, even though it has been very successful in the past, I think has some problems. One of them is that perturbation theory breaks very quickly as soon as you enter the quasi or nonlinear regime. And there's a lot of progress being done on this, and perhaps you can use resumations and higher order flavors, but one of the problems is that as soon as you start going to higher orders, then you start introducing new parameters, and all your predictive power actually gets at least diminished. And then galaxy formation and all baryonic physics cannot be really fully captured in this formalism. And of course, if we have only analytic functions describing the correlation functions, we are limited to a small number of observables. And it's very hard to model the survey geometry, and well, we have other problems. So the question is how can we make progress to increase our chances of discovering new physics? So this is a question I've been playing with over the last couple of years. And one thing I was actually thinking, is that now we know how to actually predict the universe very accurately. Dark matter simulations with treatments of how galaxies form and how gas co-evolves are actually pretty good at describing the real universe. So I was wondering, can we use directly these simulations as the central part of all this large structure analysis? And then I started thinking of what are the problems that we need to solve for that to be the case. Right, so first we need actually very efficient algorithms to simulate the density field, as Gigi was mentioning. Running one of simulation that matches the requirements of future surveys is a huge computational challenge. We need essentially huge supercomputers. Running thousands of them is really out of the question. So we need to actually be able to cover then very efficiently the whole parameter space. We need to reduce all the statistical noise associated to simulations, because we are only following a small region of the universe that actually has some noise associated to it. We need to understand and model baryonic effects, and of course, follow galaxy formation. So this is actually what me and my group in San Sebastián, here in the northern part of Spain, are trying to do. These are Mateo Senaro, who is focusing on modeling neutrinos, Marcos Pellejero, who is trying to extend our formalisms with machine learning, and also is an expert on data analysis and data inference. Then Sergio Contreras is working on modeling the galaxy halo connection, and Giovanni Ericot, who is focusing on baryonic effects. So I want to mention briefly the work that we're doing. So for the first topic, we have developed a new embodied code that was being tested up to 10,000 cores and several terabytes of RAM, which we have improved the accuracy in several aspects in the way that the 3PM force split is done and the kick and drift operators. We now do as much of the analysis and post-processing on the fly, because the simulation typically could generate petabytes of data, so we need to do things on the fly. We model directly neutrinos. We're actually modeling the full phase space through some tricubic Lagrangian tessellation. Talk about that. And also we follow the tidally destroyed subhalos, so we can actually follow and have more accurately the orbits of galaxies inside dark matter halos. So just to give you an example of this, one of the recent developments we have done is on improving the one of the most popular subhalo algorithms. So this allows us to identify and track substructures much more accurately over time. So this is showing you the mass of different subhalos as a function of time, this snapshot number. And you can see that halos grow, but sometimes they can decrease in mass, increase, decrease, and increase. This is a purely problem due to algorithms, and that is actually very hard to track these objects when they go through high density regions. So now we have changed this core algorithm, so now we can track much better this mass growth, for instance, and the evolution of also subhalos, and we can swap and forth. So now we have a better description of all the structures. So now we need to cover, now we have simulations, we know how to do them very efficiently, very accurately, but we know how to do only one of them. So what do we do if we want to sample the full parameter space? So there was an idea I proposed a few years ago, in which we take a single simulation and then we manipulate the outputs of it such that we represent the structure formation in different cosmological parameters. And this is an example of how it works. On the top panel is a box of 200 megaparsec aside, and this shows the spatial distribution of subhalos above certain mass threshold. And this simulation in particular took about 200,000 CPU hours. And the bottom is the predictions from this algorithm that took only 4 seconds. So you can see filaments, voids, clusters are reproduced pretty well. In particular, we have a roughly 20 kiloparsec errors in the positions. But we can do this 8 orders of magnitude faster. Several groups around the world have implemented it, and now it's been tested for a bunch of different summary statistics, and now recently with Matteo, we extended it also to account for massive neutrinos. I think I'm gonna skip this. So now we need to, we have a simulation, we are able to change the cosmology as we please. But still we have the problem of that we have only one simulation, right? There is a lot of noise associated with this finite sampling of modes. So we solved this problem in a paper with Andrew Ponsen. So the idea was to take not just any Gaussian random field, but we take the Gaussian random field that best predicts the average properties of the universe, and then we exploit also some symmetries in the phase fields. So this is how well it works. So this is the correlation function times r squared as a function of scale. So here you see a bunch of gray lines. This is this is an ensemble of 1,000 simulations with different initial Gaussian random fields. This is for the monopole of the correlation function, and this is for the quadrupole, so something that has to do more with redshift distortions. And here you see the symbols are not actually the mean, but are the predictions of one of these of this method. So typically we get an error is comparable to having run hundreds of simulations, and also a few groups around the world now have tested this method, and so far I think there's no bias of any sort that has been measured so far. So why this is a good idea? I wanted to spend a few minutes. This is not very intuitive why this works, but now you can imagine that you do a perturbation theory up to infinite order at a field level. So we have a particular initial Gaussian random field, but for the actual set of phases and amplitude, and now we carry out perturbation theory. And then we ask, what are the sources of discrepancy between a particular realization and ensemble mean? So then we can realize that, there are actually different terms that have similar structures. So some of the leading order terms that contribute to the noise are when two modes couple, and they have this type of structure. Then you have also terms involving couplings of 4 modes and 5 modes, up to infinite modes. But if you realize that there are sets of phase transformation, like with rotations of plus pi in the phase field, that actually leave all these terms invariant, modulus, minus sign in front. So there is actually a huge cancellation of noise terms that you do when you have this, when you apply this method, and that's why actually it's a good idea to do it. We have other problems now, and now we know how to simulate well a region that is representative of the universe, that would allow us to make predictions for surveys that would be essentially as big as hundreds of gigaparsecs. But now we need to focus on the physics, right? And there are two aspects of the physics that we need to care about. One is how to model baryonic effects, and the other is galaxy formation physics. So if you think about baryonic effects, I think there are 4 different aspects to it. One of them is that there are gas and stars at the center of dark matter halos that enhance the density. Then you have a gas in roughly hydrostatic equilibrium. Then you have a fraction of the gas that was ejected, probably due to supernova feedback, or at least that was stopped from being accreted. And that, so the halos typically tend to be less massive, and there's gas being pushed even beyond the virial radius. And then because the potential changes, the dark matter also responds to that, to those changes. Right, so the idea is that we can now parameterize all these physics, all these physical processes, and now modify the positions of the dark matter particles to be in agreement with whatever model for gas physics that we want. So with this way, we can explain essentially the effects on the power spectrum. So this is showing you the modifications to the power spectrum with respect to a case in which we have neglected all these baryonic effects as a function of scale. So typically, what you have is that there is agreement on large scales, there's a strong suppression, then a plateau, and then an increase. So we can understand this now, like the scale in which the transition happens to occur is roughly the scale in which the gas is ejected. How much it's suppressed is related to the amount of ejected gas and the back reaction to the dark matter, and the increase on the small scales is due to adiabatic contraction of the central galaxy. So we can put now together this model with our algorithms to sample cosmological parameter space, so we can do joint fits of cosmology and galaxy formation and baryonic physics. And this is actually, I think it's quite interesting because we are now fitting, of course, there are degeneracies, right? So the suppression on small scales could be due to neutrinos, or could be due to a very strong AGN outflow. But the important thing is that now we are dealing with physical parameters. So the same ones that introduce changes in the power spectrum show up on many different observables in the thermal SE power spectrum, in the cluster number counts, or on the galaxy distribution. So what we are doing at the moment is to perform joint analysis where not only lensing lensing data is included, but also thermal Sunyaev-Seldovich effects and galaxy clustering. And the final problem is now we need to understand galaxy formation physics. So now, because we have the full region of space where we resolve subhalos and merged histories, we can actually model galaxies in different ways using HODs or semi-analytics or some more complicated empirical processes. But one that I've been focusing on is in subhalo abundance matching. So this is a technique in which you just rank order galaxies, and you rank order dark matter subhalos, and essentially you say the 10 most massive subhalos are going to live in the 10 most massive, 10 most luminous galaxies and the 10 most massive subhalos. So this is an idea that I tested with my former student, Jonas Chavez Montero. So we implemented different flavors of abundance matching, and we compared with the results of full hydrodynamic simulation, in this case of ISIGO, And in particular, we developed one abundance matching flavor that we think is the best. And we can predict now the spatial distribution of galaxies. This is in real space, and this is in redshift space, roughly above 1 megaparsec with an accuracy of a few percent. On small scales, actually, the differences could be huge. And actually, we track down to the details of how you actually treat tidal stripping of stars inside larger dark matter halos, or how you assume, or the efficiency of run pressure in stripping cold gas from galaxies. In other words, how quickly you're going to shut down the star formation when galaxies fall into larger dark matter halos. So this actually is a topic that usually is neglected, so the importance of galaxy formation. And I think this is going to be quite important for the future surveys, because this modulates the way in which we sample the density and velocity fields. This is an example, for instance, of it's an illustration of how we expect galaxies to be inside dark matter halos if you select them according to stellar mass. These are roughly a distribution which are centrally peaked, and they have roughly virial motions in equilibrium. But if you look at emission line galaxies, for instance, the picture is very different. They're located mostly in the outskirts, and they have net infold velocities. This is because for a satellite galaxy to be still star forming, they need to or to be detected as emission line, they need to be star forming, and for that they need to have cold gas and actively forming stars. But typically the gas is being stripped and star formation shut down earlier than, or in shorter time scale than one one crossing time scale. So only with the galaxies that just falling in, the ones that are going to be detected by surveys. I told you how we can actually improve the modeling, the current state of the art of the modeling in several aspects, but no modeling is or will ever be perfect. So there are issues regarding the numerical accuracy in which we solve, how we solve the equations of motions in numerical simulations. We still have a finite mass and volume. We have issues related to structure finders, merger trees, or we know that our treatment of galaxy formation and baryonic physics is approximate, and also the errors associated to the way we sample cosmology. So currently, people, when analyze surveys, assume that the model is essentially perfect up to some scale, and then is absolutely incorrect after some scale. Right? I think, as we've been seeing here, I think errors are actually better behaved than that. So what we're pursuing is to actually rewrite the livelihoods, taking into account all these errors in the theory that we are assuming, that we are actually measuring and quantifying. Right? So now we have a data vector, and we have a given model, but we know that there are some errors associated to that model, and we can fold that into and then marginalize over model errors, and we hope to give much stronger constraints. Okay, so how much time do I have? 3 minutes, okay. So the summary so far, I think, is that we're soon going to be able to analyze large-scale structure data with a physical modeling. I think this is the most important thing, where we can be able to predict directly density and velocity field of individual objects and for the full three-dimensional distribution of gas and stars. We can have individual properties for these individual galaxies, and this would be, I think, quite important, because you would be able to make predictions for any clustering statistics, for any observable that you can think of, and the same physical process parameters would be projected into different planes, and there would be a kind of a more holistic description of large-scale structure. So just to finish, I wanted to give you another hint of why this is also so important. This is I took a sample of galaxies modeled according to Sham, with a number density in between what LSST, the billion object apparatus, or Sphere X will measure. And this is, so this is the error that your model is making as a function of scale. Right? So linear theory actually is accurate only on very, very large scales. Very quickly, it kind of goes really bad. The target of perturbation theory is to get to 0.2. The most optimistic claims get to 0.4, something around this regime, but with a lot of free parameters. So in this approach I've been telling you, actually you get roughly 1% precision all the way up to K of 10, and we are actually limited limited by our galaxy formation prescriptions, not by the way in which we solve our equations. So, and this is actually quite cool because could actually translate into better physical constraints. So this is a Fisher matrix forecast on how much better we could do if we are getting even up to K of order unity with the simulation-based modeling for some FNL parameter, the growth rate, and the mass of neutrinos. This is relative to what you would get using perturbation theory, so stopping at K of 0.1. So we can see that actually for the case of neutrino masses, you can even get constraints that are up to 30 times stronger than what we currently get. So I think this is not only, it's another big motivation for us that we can actually, maybe there is actually science already of massive neutrinos in current data sets, and we are just not able to extract it because of our inability to model it. And okay, so, I mean, this is not something that actually will be done in the future. Actually, we already did the analysis of the CFHT lens data, and I'm just going to give you that cosmological constraints. And this is actually the spin 2 field split into two orthogonal correlation functions. This is the data. Now the solid lines are actually our best fit model using directly essentially the statistics measured in these three-dimensional simulations. So this is, I think, as far as as far as I know, the first time that cosmological constraints are directly extracted using essentially the comparison of millions of this simulated universe with the real one. Okay, so I think I'm gonna finish this, and I'm happy to take questions. Thank you.
Yeah, time for questions.
Do you have if you go back one slide to the CFHT lens analysis, do you have a comparison of what it would be with like linear theory scale cuts and whatever the previous analysis was? Right. Just to get a sense of how much the contours shrink.
Actually, they don't shrink much. So the reason why they don't shrink much is because the nonlinear power spectrum in real space is one of the things that probably is best calibrated with the different halo feed or emulators. So for that, they actually make pretty accurate prediction all the way into the nonlinear regime. So I think our advantage there is that then we have this self-consistent treatment of baryons, and then we can take this lensing and then do a cross correlation with galaxies, so galaxy-galaxy lensing, and then something that it would be very hard to do with these calibrated fitting functions. But for the sheer power spectrum, the accuracy is almost identical. Yeah.
I have two quick questions. One, I hope you can answer in a very short order. Rescaling is too magical. So where does it break down? I can't really see how you can do it given the nature of the neutrino transport, for example. So there must be some kind of measure in which you say it's good here, but not good for other measures.
Right, yes. So actually, this is also something we're working a lot on, is to characterize uncertainty associated to scaling as a function of cosmological parameter space. And so the short answer is that the error increases the further you go away from your original cosmology, and the error is worse for the very central parts of, essentially for the concentration mass relation. We have worked out corrections for that. But in any case, that actually is almost irrelevant for the galaxy clustering, because essentially you are going to be predicting correctly the mass and where the structures are. So yes, they're going to be slightly more or slightly less concentrated, which is important for lensing, but not for galaxy clustering.
Well, I have very many questions on that, but I won't ask them right now because I wanted to slip in one other question. When you're doing subhalos are not stable entities and they get split apart and all of that. When you're doing galaxies, it's a different thing because we've got baryonic concentration. So abundance matching can't work that well unless you do a lot more detail with the end body history and all of that to try and compare. So you did and showed that your sham bad choice of terminology, by the way. Your sham approach and the Eagle galaxies actually did very well. So maybe you could comment on that, why that works?
Right.
'Cause
So
I just don't see that it can work
right.
that way.
So I completely agree with your statement. And then, so the way we are tackling that issue is by actually, so as we follow the simulation, we're actually also modeling the subhalos that were tidally disrupted. So and then the dynamical friction timescale is another part of our modeling. So in that sense, it's more robust. And the one in Eagle works because the dark matter mass resolution is much below than the typical subhalo mass hosted by the galaxies that we're looking at. Right? So this, so still essentially 99% of the subhalos with a galaxy that you expect to have a galaxy are resolved, which would not be the case if you model large-scale structure, but then we need that's why we need then essentially this dynamic tracking of subhalos.
Okay, let's thank Raul. We can ask him questions in the coffee break.